So today I will talk about load reserve store conditional wait. So like a new load reserve store conditional variant that we implemented recently to enable scalable and efficient synchronization in like very big, massive like Manycore systems and by making it polling free and retry-free. So essentially the issue we have with all modern like parallel systems is that we require synchronization, require access to a shared resource. And usually we have lots of cores, lots of memories. And then, for example, somewhere in one memory, we have a lock, and we can access it through atomic operations. And one of the cores will acquire the lock, of course, and then can continue in its critical section or something. But then what happens is all the other cores will continue to poll this lock and will interfere with the core working, will waste a lot of work. So this will decrease the performance of our system. And this is especially amplified in like cashless systems where we don't have the coherency protocol helping us out by building like queue locks and stuff. So one alternative is non-blocking algorithms. So we don't have a lock to spin off on, of course, but we still need some atomic operations, usually load reserve store conditional. This is what we will look mainly at in RISC-V, but also compare and swap. So it's a similar concept. But here we still have a similar issue because, for example, here we have A, B, and C, 3 cores. They will issue some load reserved and store conditional pairs. And only one of them can succeed because, I mean, it has to be atomic. So the first store conditional of core A might succeed, and then the other 2 will fail. And what will happen is that the other 2 have to retry again. Maybe C will fail again, and then it has to retry again. So we still have this polling retry mechanism, even though we are in the non-blocking algorithms. And essentially what we would like to have is something like load reserved wait, how we call it. So a new atomic, where we, instead of ordering all the atomic operations at the store conditional, so instead of checking there who won the race, let's say, we do it already at the load reserve. And we let B and C wait until A's store conditional is done, and then we proceed with C and then with B in this case, so that we have much less polling and retrying. And as an additional benefit, we will get better fairness and performance. So what we'll talk is essentially this new atomic load reserved wait, store conditional wait, which will give us better fairness, performance, and so on. But we can also talk a bit about this, weaker progress guarantees, and then specifically also about the Colibri, which is like a scalable implementation of this scheme, leveraging a distributed queue. And then, of course, we'll evaluate it on one of our architectures. So in an ideal load reserved wait, what we do is essentially we use a queue instead of a table to track reservations. So usually for load reserved store conditional, you have a table where you track which cores have a reservation. What we do instead is essentially we bring order into this table and make it like, give it an ordering. So when core 0 here issues a load reserved to address A, it will get the response, it will get the value of A, and it will be put into a queue. And similar for core 1. And now compared to a table where this would happen in parallel and every core has like the same priority. Here we have core 0 at the head of the queue. And what this means is that we withhold the response to this load reserved for core 1. So core 1 does not get a response. It does not get the value of A because it is not at the head of the queue. And we do this until core 0 issues its store conditional. Then we can remove it from the queue. We can update the memory. The store conditional will succeed because no one else interfered. And then we issue the response to the load reserved wait to the core 1. And then it can also issue its store conditional and succeed at the first try. So this requires no polling, no retries. But the thing is, I mean, queues are super expensive. And if we have multiple memories, such queues can get really and many cores, because we need one entry per core, these queues can get huge. So what we do essentially, so we move from load reserve to load reserve wait, where we move the reservation table that we have one of each at each memory bank. So this is like complexity n times m with n cores and m banks. We move to load reserve store conditional wait, which has the same complexity but in queues. But to reduce this complexity, we will now introduce Colibri, where we essentially move from a hardware queue to more of a linked list scheme in hardware again still, and then reduce the complexity drastically because we just need one node per core and some pointers per memory. And how this works is more or less like this. So every memory gets a controller with a head and a tail pointer. Every core gets a node with a pointer, and initially, I mean, here now they're all null pointers. Let's say they don't point anywhere. But then when core A, for example, issues a load reserved wait request, it will enqueue itself in the memory. I mean, the queue now has one single entry, and it will immediately get a response because it's at the head of the queue. We can then have the same for core B. So core B will enqueue itself, but now it will just update the tail pointer. So this is really like a linked list, but all of this, these requests, they just go through an interconnect from core to memory in actual hardware. And similar as before, we withhold the request to the response to B, but instead to keep the queue intact, because B is now the tail, so we updated the tail from A to B, we have to let A know that it will now point to B. So essentially just keep a linked list. And we do this through a specific successor update, which we also send through the interconnect. At this point now, maybe for A issues, it's store conditional. So it completes its operation. And to keep the queue intact, what happens is, so it will be removed from the head, but it also, since it is the only core knowing which, which core will be the next one in the queue, it has to send this information to the controller as well. So with the store conditional, we also send a wake-up request, which essentially communicates the successor of A to the controller, so B can now be the new head. And at this point, since B just became the new head, it will also get the latest value of the memory. It will get its response of the load reserve wait, and then it can do it can also complete its store conditional wait. So we implemented all of this on mempool, one of our Manycore architectures, where we have 256 RISC-V cores sharing a single shared memory, which consists of 1,024 banks. So you can see here that, like, if we have at 1,000 banks queues of 256 entries, this is really a huge overhead. And that's why this Colibri scheme is so useful. So we benchmark it with first just a synthetic benchmark where we just want to see the throughput. So we have like a histogram where we atomically update a histogram, and depending on the number of bins, we can kind of control the contention. So if you only have a single bin, all of the cores will always update a single atomic variable. If we have lots of bins, the contention is distributed across all the banks, which essentially means less contention and less conflicts. And we can see, so just as a reference, we have the atomic add, which is kind of the, let's say, almost ideal implementation of this. It's just a single cycle addition directly at the memory. So this can be seen as our roof line. And then we have in green, the load reserve store conditional wait implementation. So at the top, the ideal one. And then we also have somewhere we have a shorter queue. So instead of having a full queue, we only give, let's say, 128 or even just one entry in the queue, essentially letting everyone else fail immediately. And then you can see that in red, we have Colibri, which has this the same complexity roughly as load reserve store conditional wait with just one entry in the queue, but it performs very closely to the load reserve store conditional wait, the ideal implementation essentially, where we would have these huge queues. And the small difference just comes from the fact that we need to send those little messages to keep our list alive. So then comparing to load reserve store conditional, we can see that we outperform the load reserve store conditional, especially at high contention, by a factor of 6 here. And yeah, we are very close to the ideal. So if we then use something like a concurrent queue, where we have just all of our cores, or we sweep our cores, but have them access a concurrent queue, NQ and DQ, some stuff. The difference the atomic add, so just a locking queue in yellow. And we also have kind of the standard deviation of the cores to see the difference between individual cores. And what we notice is, so first of all, Colibri outperforms all the other schemes consistently. And we notice that at high core counts, when congestion gets really high, we have less queue access per cycle, even though we have more cores working on it. So we really see that we have this interference issue, but Colibri stays so its throughput stays high. And then the other thing to notice is that Colibri's, the deviation between the cores is fairly small compared to load reserve store conditional, for example, where we have this huge, I mean, the blue doesn't even fit in the plot anymore because some cores have much more accesses to the queue than others. And with Colibri, it's rather fair because we order it already at the load reserve. So yeah, we have a very fair scheme compared. And yeah, one other thing, we'll not go into too much detail, we also measure the energy efficiency and power and so on. And the thing is, this leads to a huge improvement also in energy efficiency because we have less polling. So finally, what we will also look at is the interference. So we kind of saw it hinted at in the previous plot, but then we measured it explicitly in this scheme where we have some cores executing actual work, and then we have some cores disturbing them. And in this case here, we can see that for Colibri, so the red line, the relative throughput, so depending on how many cores are polling an atomic and how many atomics we have, for Colibri, it doesn't matter. We always, we never disturb really the worker cores. We always get the maximum performance in the workers. For load reserve store conditional, it's a different story, especially at high contention and with lots of core interfering. We can see that the relative throughput is drastically reduced. So yeah, we see like up to a 3 times reduction in performance if we just have so unrelated atomics going on and congesting the interconnect through their polling. So yeah, I mean, that's more or less it in conclusion. So we just proposed this load reserve wait, store conditional wait, which pretty much outperforms load reserve store conditional across the whole spectrum by eliminating the polling and interference of working cores. And we propose a scalable implementation of called Colibri of this scheme, which drastically reduces then also the overhead that we need to pay in hardware.